Hello and welcome back. In the last video we defined work with the symbol W and said it was equal to force dotted into displacement. So if I'm talking about the work done by a specific force, I take that specific force and I dot it into the displacement the object experiences as that force acts. And remember that the dot product is treated a very specific way. I multiply the magnitude of the first vector, which is F, magnitude of the second vector, which is D, and I multiply that product by the cosine of the angle in between the two vectors, force and displacement. Physics is a series of telling less and less lies, and this is a case where we made a simplification. Mother Nature is pretty complex, and so when we first introduce things, we try and introduce them in a very simplistic fashion, and then we try and layer more and more complexity into it. And so it turns out this equation, work equals force times its displacement times the cosine of the angle between the force and the displacement, is only valid if the force and the angle between the force and the displacement are both constant. Okay? So it's the only time that we can use this formula is if both the force and the angle between the force and displacement, both of those have to be constant, neither one varying over the displacement. More generally, how do we calculate work? What if the force isn't constant? What if the force is changing over the displacement? Force is becoming larger over the displacement, as is shown in this graph. So I have put position down here on the horizontal. Remember, position symbol X. Force is on the vertical. And I'm labeling, or I'm showing some graph which I have drawn as a line with a slope here. Notice that the force starts off as 0 at the initial position, but what happens to the force as the displacement is increasing? Notice the distance between the initial and final is the displacement. And so as the displacement's getting larger and larger, the force is also getting larger and larger. So this is a case in which the force is not constant. We cannot use this equation under those circumstances. The real definition of work, the valid, always true definition of work, is that work is equal to the integral, and remember, integral just means area under the curve on the force versus displacement graph from some initial position to some final position. So here I have drawn the triangle clearly so that you can see by putting the dotted line down and then kind of shading in the center here, that area. That area is a triangle, and that magnitude of that area represents the work done by this force over this displacement. So work is actually equal to the area under the force versus position graph, and this is always true. If it's a geometric shape that we know how to find the area of, then it doesn't matter whether the force is varying or not. We can still calculate area as triangles or rectangles or semicircles. Geometric shapes we understand how to find the area of. If not, if it's more complicated, then we're going to need the integral to actually calculate the area under the curve. Now let's look at the sign for work. When are we going to have positive work and when are we going to have negative work? Well, look at the angle theta. It's really the only piece that can possibly bring a negative sign. When we're talking about the magnitude of force and the magnitude of displacement, those quantities are always positive. So what's going to determine the sign of work is the angle theta. So theta, which is the angle between F and D, is the sole determinant on the sign for work. If theta lies between 0 and 90 degrees, 0 degrees and 90 degrees, then cosine theta is greater than 0, and subsequently work is greater than 0. If theta lies between 90 degrees and 180 degrees, then cosine theta is less than 0 and work is less than 0 as a result. Now, what about the special cases? Well, what about if theta is directly equal to 90 degrees? Then cosine 90 degrees equals 0 and work subsequently equals 0. So the only time a force does not do work is if it is oriented at an angle of 90 degrees with respect to the displacement of the object. So for example, an object, let's say, is on the floor, and we know that there is a normal force acting on it that is exerted by the floor on the object, and let's say the object is displacing in this direction. So there's the displacement and there's the normal force. Notice that the normal force is at a 90-degree angle to the displacement, so the normal force does not do any work on this mass as it moves across the horizontal floor here. The normal force is not doing any work, okay? However, you know, some entity that may be pushing on this mass is of course doing work, and if there's friction on the surface here, then friction will also be doing work. The only time a force does not do work is when that force makes a 90-degree angle to the displacement of the object. So this gives us a little bit more to work with, if you'll excuse the pun, as we look more and more at our studies in work and energy. And in the next video, what we'll do is derive a very important theorem that will serve us really well and make many of the problems that we look at much easier to analyze. So that'll be the next video. We'll see you then.